Okay, now let me take up uh, the two very important concepts in electromagnetic waves is that of dispersion and absorption, especially in a medium, okay, in a material medium. Let me first give an example of what is a wave packet. You know the idea that say sine wave or a cos wave is a pure wave. In a way, it is a myth because a sine wave, if it's a pure wave or a plane wave, it's a complete plane wave is a myth because it has no starting, it has no ending, and it is not supposed to encounter any obstacle or be disturbed by anything. Such a thing is something like almost at the status of the god, right? Anadi, Anant, and nothing can change it. So those concepts of that's a pure sine wave and cos wave is in a way it's a myth. So everything else that we deal with is indeed a superposition of sine wave and cos wave or plane waves. Okay, and you will learn this a lot more about in Fourier analysis that we are going to do in your maths course. But let me try and give you an idea of a wave packet by the elementary example, which you am sure you must have done in school also. Okay, that is, if I have two waves, let's say cos, the center wave is k and displaced it slightly by delta k, and its omega also by half delta omega. All right, and then I take another one, which is this is plus, and there I take it to be minus, slightly off from the center frequency k, and this is slightly off by minus half delta omega. Okay. Now, if I add them up, okay, then I'll get phi 1 plus phi 2 is simple trigonometric operation, cos A plus cos B, and I can write down in terms of, so you can see that I chose is half delta k and half delta omega, so on, such that I get my carrier, okay, as cos kx minus omega t, but it is modulated by a slower moving uh, cos function. Let's see it in a figurative. Suppose this is the blue one and the red one is slightly off by half delta k and half delta omega. All right. So you can see that when they peak, for example, here, they're absolutely they're in on top of each other. Okay. And here, when they go to, they cancel each other completely. It is here. Blue and the red completely cancel and it is zero. So this cos kx omega t is the original, this is the wave. Okay. And the this dotted line, the dashed line, is the one which is this cos half delta kx minus delta omega t. All right. So superposition of just two waves has now given me what I'll call a wave packet. The simplest example of a wave packet. There's a beat. Okay. So, and then I can see that as if this wave packet is moving. Okay. So this is indeed familiar to us. Okay, this is what the concept of heterodyne. And for example, this frequency omega is the probably your radio station, and the music that is coming on is riding on top, which is much slower. So and that is we know is super. So if I now want to have a packet which is very compact, like a pulse line, then I would require a lot more of these waves to be added up with the proper amplitudes, and I can create any kind of wave. So that's an example of a wave packet. But the point that I want to make is how fast does this peak move now? Okay. What is the velocity of this peak if I say that this packet is going to move? Okay, that I can find out because the modulating envelope, that is the dashed line, the position of the peak is given by delta kx minus delta omega t must be zero, because that is what it becomes, cos kx minus omega t. Okay, and so that is delta kx minus delta omega t zero is the how I find out where is the position of this peak. And then if there is a slight change, then therefore the increments in x and t at the position of this peak I can give by delta kx dx and delta omega dt, and that must be also 0 after dx by dt when it has moved, okay, in space. So that is going to give me what is called the group velocity dx by dt, that is delta omega that I've chosen by delta. So this is the speed in which this packet, this whole one packet from 0 to 0 is actually moving. A packet is moving. And hence we call it as a group velocity, as if this group is moving with this velocity. So and I can now just take delta omega delta k to be very close, and then of course there's a definition of the group velocity. So we have the phase velocity. Phase velocity is nothing. This is not physical. This Vp omega by k. Okay, this is just defines how the phase of a plane wave is. But the actually something is moving, a signal is moving, or energy is moving. That would be moving with the velocity of the group velocity. All right. So I hope this is good enough for us at the moment. It's an extremely important concept because group velocity is the one which finally in quantum mechanics or in anywhere else is the one at which the energy is moving. Okay, the actual or the signal will move. In some cases, the phase velocity can be larger than light, but that's not the signal velocity. Signal velocity will always be the group velocity. Okay, so let me come to the concept of the dispersion. What is dispersion? Just by definition, it is the frequency dependence of speed in the medium. Okay, in air or vacuum, all the wavelengths of light travel at the same speed c, and hence air or vacuum is a non-dispersive medium. But in a medium, if the wavelength or the frequency is or the speed which is is moving is dependent on is dependent on frequency, then that medium is called a dispersive medium. Okay, let me give you an example. For example, we know that in air it is a non-dispersive medium. This whole is white because all the constituent colors of visible light is giving us an impression that it is white. Okay, but once it get into the glass prism, then the glass is a dispersive medium, and there they travel at different velocities. Why? Because the refractive index for each wavelength is different. Okay, so they will travel at a different speed. Okay, and the one that is so that is why the bend. So this prism was made in such a way that they'll emerge by showing up their differences in the speed in the medium. Okay, and that is how we get red, the VGR out of the white light. Okay, Newton's discovery. Okay, so and that is because the main reason is these are different kinds of glasses that we use in optics. Okay, this flint glass, barium crown, borosilicate glass, the fluoride crown. In all of them, look at this refractive index. As the refractive index is with lambda, refractive index decreases. The refractive index and this lambda. Okay, and that is why they have different speed in this different each of these lambda will have different speed in the medium, and that is what is a dispersive medium, example of dispersive medium. It also happens I can as I told you, I can compose a lot of harmonic waves to make this pulse. Okay, but inside this pulse all these harmonic waves could be traveling at different velocities, their phase velocities. So after some time, for example, this will spread because the faster ones will move faster, and the slower ones will be moving, lagging behind, and hence this pulse will spread. And in communication, it is very, very important. If I send two pulses, 1 0 and 1 1, if they spread and they start joining, then your information is lost. And that is why we have repetition of the optical signals in a fiber at a very short, very frequently before it reaches so that the spreading is not such that it is totally lost. The information overlaps and is lost. Okay, so it can over time, it can in space in some way. So these are the examples of dispersion. Uh, my question paper for the class, okay, is also a tool for dispersion of hard work and motivation. All right. So the question paper is designed in such a way that the hard work people get different kind of marks, and people who are neglecting the course get different kinds of marks. In that sense, a question paper is a tool for dispersing the class performance. Okay, so wave packet is, you can always consider it to be a group of harmonic waves of different k, of different lambda, of different amplitude, and this is what Fourier told us. You can always, any continuous a kind of signal you can compose uh, simply by a summation of harmonic waves. Okay, for example, phi xt, it could be a complex, okay, and then different amplitudes, and you could make it. So that's the wave packet. Or if it is so close that you could actually simply integrate it. Okay, that is for a amplitude is for each k, and then you suitably uh, take the number of k's and integrate it, okay, to get a signal. That is what is the wave packet is. And but omega and k, this relationship, what is the relationship between omega and k, that defines the medium. Okay, for example, omega is equal to ck is the definition of a non-dispersive medium, as in vacuum. Okay, they're all, omega is equal to ck. So every wave has the same speed, that is non-dispersive. But this relationship, okay, if you want to specify that the EM wave is traveling in such a medium, then you have to specify the relationship omega k, and that is nothing but omega is a function of k, and that is why this is called dispersion relationship. Okay, so defines all about the medium. In fact, quite often when we study solids, for every excitation, all we want to know, for all kinds of excitations, all we want to know what is omega as a function of k, then we can predict whatever happens in that medium. Okay, so let me take a simple example. You might have done this in a dispersion of water waves in deep water. We know the omega dependence of wavelength. Okay, and that is given by omega is equal to root over gk, where g is the acceleration due to gravity. Okay, and k is 2 pi by lambda. So this is a dispersion relationship. Okay, and this is a dispersive medium because it is not simply proportional to k, which is k to the power half. Okay, and so this is the phase velocity is omega by k. The phase velocity is of course g lambda by 2 pi. Okay, which means that is the, in the water waves of longer wavelengths, okay, have greater velocity, and if the wavelength is smaller, then they fall back in terms of phase velocity, and hence if there is a group, then there will be dispersion, and we can find out of Vg, the group velocity. Okay, the surface of water waves is a dispersive medium, and we can find out what is the Vg. Vg is d omega by dk, and I can just simply uh, d omega by dk, and it's half root over g by k. And you can see that in this case, the group velocity is half of the phase velocity. All right, this is just an example. For example, in a free particle in quantum mechanics, you will see that omega h cross omega is p square by 2m, or h square k square by 2m, and hence you can find out d omega by dk, that is k square. Omega depends on k square. Here it is omega depends on root of k. So different medium can have different dispersion relationship. Now, characterizing waves in a medium, okay, let me amplify this a little bit. If it is a particle, we know that normally when in dynamics in physics 102 you would have done x of t. If I know for a one dimension a particle's position as a function of time, okay, that is kinematics, then I need to know x as a function of t to able to predict where it is or what is it doing in the medium. Okay, so it's dx by dt is velocity, d square by dx dt is its acceleration, or in different, if I am doing dynamics, then if I know the acceleration, I can try to find out the force, and from there I can find out what is velocity and x. That is what we do for a particle. What about a wave? Okay, wave in a medium. Wave is traveling, it has a velocity. What do we do? Okay, we do so wave it is, but the wave is characterized by uh, these harmonic waves. Each of these harmonic waves have a time period and a wavelength. So instead of x and t, we have the lambda, okay, which is the repeat period in space, and capital T is the repeat period in time. That are the two things that is I know about the wave, and hence I try to construct two. This is 2 pi by lambda. You can, okay. So instead of x, I is 2 pi by lambda. So I have kept it on the x-axis such that I can still have my velocity as the slope 2 pi 2 pi by t. Okay, so instead of, for a particle we have x and of t, for a waves we have 2 pi by t by 2 pi by lambda. This is nothing but omega, and this is nothing but k. So omega k relationship tells you, okay, the about everything that we want to know about the wave in that particular medium. For example, this is one particular omega versus k, let's say. Okay, then so this is the phase velocity, okay, which is not the actual velocity. This is just a definition for the phase, but the group velocity would be d. So anywhere you take this, take the slope at, you can say that those groups are traveling with that velocity, and that is the real velocity. This vg cannot be more than c, okay, the speed of light. In fact, this is such a wide concept that I want you to understand. For example, if I am doing quantum mechanics, then h cross omega is E. Okay. And this is h cross k is 2 pi by lambda. H cross 2 pi by lambda is h by lambda, which is p. So is really the dispersion relationship is a relationship between energy and momentum. For a free particle in classical mechanics, E is equal to p square by 2m. It will be parabola like that. E is p square by 2m. So dispersion relationship defines how that particular packet, wave packet, is behaving in that medium. Okay, so this is energy and this is momentum. In fact, all our solids, when we study, you will know everything about the solid. If I know what is in that solid, is E as a function of k. Okay, k is standing in for momentum, and E for energy of the electron or the carrier. Okay, so that is what the idea of a dispersion. With that, let me go to the simplest possible model of in a solid of a complex polarization due to bound electrons. And the model that you'll be familiar with is a simple harmonic model. Okay, model is simple and using simple harmonic motion. That is what I meant. Okay. So if electric field is traveling in V, then I can model the bound electron. I am talking about the bound electron as if it is bound to the atom. Okay, where whatever is bound to through a spring. So if it has a mass, then omega is root over k by m. So it is the so model of the bound electron. Okay, this it is a very simple model, and that is why sometimes I call it is the proverbial physicist spherical approximation to a resource. Okay, so if a physicist wants to model a resource, his first assumption is the resource is a sphere. It's at that level, but yet it gives you results which can be compared with experiment. It's a very powerful, simple models are very powerful mental models. So let's, you are familiar what I'm going to do with in from your physics 102. You have done forced simple harmonic motion there. So I can write down the motion of the bound electron by m acceleration, and the gamma is the dissipation. Okay, m gamma. M omega naught square is natural frequency, root over k, omega naught is root over k by m, and I'm forcing it by the E field. This E is a mistake. So Q E naught cos omega t. All right, ignore this E. Okay, that's a mistype. So I'm driving this. So this is a mass spring system which has a dashpot also. That is, it has a some way of losing energy as well. Okay, and I'm driving it with a forcing function, harmonic function. So omega is the forcing function, that is the in this case it will be an electric field of the light. All right, and this is the natural frequency. Omega naught is the natural frequency of the bound electron. So we know how to solve this, make it complex and put e to the power I omega t into it. Okay. So, and then we look for omega dependence of amplitude of x hat. So please ignore this e, there's nothing here. So this is x complex magnitude. I then I choose this and then plug this in to find out into this, to find out my x naught omega dependence. We have done that quite number of enough. And so I've taken it instead of E with as Griffiths, I've taken it for Q. Q is any charge. So this would be Q by M omega net square by 1. So this we can solve that. And here assume that is minus Q, meaning electron, but I did not assume that. So the dipole moment of one electron will then be this Q, or one charge will be P Q x naught hat, and this will be this, right? So that is because the charge is moving around this mean position. And then this is exactly the same thing that I did, but without this term. Okay, it was a free electron. So then I can find out the dipole moment, complex dipole moment. N is let's say a total dipole moment per volume, then nq x naught, nq square by m, and this is the complex magnitude of my electric field. Okay, and what are the fj? Fj is each electron, j number of electron fraction, okay, of electrons can have a different omega naught. Okay, so omega j. So that is omega j. They can be, not all bound electrons are situated in the solid in the same kind of environment. So because their environment is different, the spring constant with which they are attached to the atom could be different. Okay, and that is j. And hence their omega j can be different, gamma j, the dissipation constant can be different, and the number of fractions like that. Then I'll sum over that, and that will still be, this is the fraction, so this is the total number is still n, this is only in terms of fraction. So there can be different types of environment with different natural frequencies, okay, and the damping constant and the fraction. So that is omega j, gamma j, and fj. Okay, so I can write down just like there is a complex susceptibility now. So polarization, complex polarization is a complex magnitude of electric field in terms of complex electric susceptibility. All right, because this I can be there because of this the dissipation. Okay, so I can now look for refractive index, which can also become complex. And so the two important constants that we are talking about is the refractive index and absorption coefficient. So let's say the polarization. Okay, I'm just repeating what I obtained there. Okay, and then this is my complex susceptibility. I can now write down my epsilon r, relative permittivity. I have also made relative permittivity complex. Okay, that is 1 plus susceptibility, and then I by, okay, so by divided by E and epsilon naught, so 1 plus chi E. So this is really chi E, so a complex chi E, and it's complex because of these factors. Okay, that is my relative permittivity now. So typically, the imaginary part is negligible unless, of course, I am close to a resonance. That is, if omega is very close to omega j, then resonance is important. Otherwise, if there is no imaginary component, then probably you already know that the resonance will take it through the roof. Okay, and so it is the imaginary component which gives a finite width and a finite amplitude to a resonance. So if I am, unless I am at the resonance, this term is quite negligible. Okay, so let me assume that, and then I can now plug it in into my wave equation. And now the wave equation, epsilon E epsilon is complex. Okay, is the old wave equation for my E, and so and I'm considering a non-magnetic material, so hence mu naught. I try my EZT in traveling in KZ direction. Okay, and of course K would be complex here, and so complex K is now simply a replace by, instead of epsilon mu naught epsilon, not mu naught, the complex epsilon, okay, mu naught omega. Okay, that will be my, so the complex K would have, let's say, K plus I kappa, something similar that we have done earlier. It's just the notation. It has nothing physically to do with the same old kappa or same old K. All right, it's just that the real part and the imaginary part. And hence, if I write down the electric field, because of this complex part, this is the imaginary part, I will get now also attenuation. This is a real decaying exponential, and hence it is getting attenuated. All right, so because of the K is complex, okay, the K complex, the imaginary part here also will give me attenuation, okay, which means I'm losing energy. So there will be absorption. Okay, so this is attenuation, and that will cause loss. And but intensity is proportional to E square. Okay, and hence I must be equal to I naught e to the power minus 2 kappa z. All right. So if I have initial intensity I naught, and if it's traveling in the z direction, then it is goes as 2 kappa. And this is an important constant called alpha. 2 kappa is alpha. That's called the, so loss of intensity is this called the absorption coefficient. This is a constant of the material for that particular frequency. It can depend on frequency, but it's a, so alpha is 2 of kappa. That is the imaginary part of this complex quantity. That is the absorption coefficient. At the same time, what is the refractive index from the real part? Ck by omega, as we know. Now these two, alpha and n, are the two most important optical properties of any materials. Okay, and we have obtained by using a simple harmonic motion model of bound electrons there. Let me continue. What happens I said I am away from the resonance, and because of that, I ignored the imaginary part, and still I got my K complex. That K complex was because there is loss, intensity loss, because of the they are not in phase. The motion of the vibration of the bound electron and the E are not in phase, and then there will be loss. And so I can now look at what happens near the anomalous. So I'm writing down my same epsilon ER, okay, old. But normally this, as compared to 1, this is normally pretty small, okay. So small as compared to 1. So with that, I can now make a simplification. My omega c is root over, okay, and I can take binomial expansion if it is sum, and then that is why I added half here. Otherwise, so this becomes a little simpler. Okay, so remember, I'm using my epsilon to be epsilon r to be complex. All right, so this half is because of the binomial expansion after considering this small, and hence I can write down my refractive index, okay, as 1 plus, okay, and omega z square minus omega square is something that you have done in resonance in 102. So in those terms, I can write it down. So I can get my n, and I can get my alpha also. Alpha is 2 kappa, okay, and that also I can obtain in terms of just the imaginary quantity, and that is omega square by omega square. So I've got an n and alpha in terms of my model, okay, my model fractions, okay. So then I can now plot, okay. So I have plotted here around I have chosen one of the resonance, let's say WJ, one WJ, W1, wherever there is a resonance. And then I've taken n minus 1, then only this quantity is showing up, okay, n minus 1, and I plotted that as a function of omega. It looks like that, okay. So this is n minus 1, okay. And then what is alpha in the meantime? This is the loss, and this is now peaking here, okay. So I've just plotted this, something similar that you would have done in resonance in 102 also. So this is the absorption dominated region. Okay, since omega matches, okay, the natural frequency omega j, so around omega j here. All right, so there the n goes down, n minus 1 goes down. So most of the time n normally increases gradually with omega when I'm far away from resonance. Okay, however, in the neighborhood of a resonance, it drops drastically, sharply from here to here, and that is why it is called anomalous. Okay, because just near the near the natural frequency for that particular mechanism or those particular electrons, there is a lot of absorption, and in that case n drops. Okay, typically n increases, here it n increases, n increases. So far from the resonance, n is typically increases, but during the resonance n drops, and that is what is called anomalous dispersion. So n runs below 1 here, which means does it mean that the velocity is greater than c? No. It's just an example. I am not taking the background into account. There is, of course, other things which are determining n. In any case, it's a phase velocity and energy doesn't travel at that speed, so that should not bother us. But that's the nature of the curve from this simple model, which you will see how it is actually in measure. So from this, I can obtain what is known as the Cauchy formula for the refraction and dispersion. So I can now write down my n. I'll make simple simplifications. Okay. So I'm writing down my n, and that I had written down in the last slide. Similarly, if I'm far away from a resonance, I've already considered the resonance anomalous dispersion. If I can okay, I can ignore the damping term. Okay, and then of course n simply becomes uh, I ignore that term, and then it just that becomes cancels. This cancels, then becomes this, and this we have also kind of done this manipulation earlier in 102 while studying resonance. For transparent dielectrics, the nearest resonance are typically in the UV, so you can actually ignore them. If we assume that omega is less than omega j because it's in the UV and we are talking about, let's say, in the visible, then I can also simplify, and this I can take this omega j square, and this becomes minus 1, and then I can expand, and that becomes 1 by omega j square, 1 plus omega square by omega j square. A simplification that I can do. So this can be now rewritten with this simplification, okay, as n is equal to 1 plus this simple by omega j square plus a term which is omega square nq square 2 by epsilon naught fj. Okay, I have taken omega common, and hence it turns out to be omega j to the power 4. But these are all constant j dependent. That is for that particular material or for particular species. What you really get n is 1 plus something plus omega square into something, which are all dependent on that particular specific material or specific situation. And hence, I can write down omega in terms of lambda, 2 pi c by lambda, and convert this into a, so this whole thing is A, and this whole thing as A into B. Okay, I can take A common, then n is equal to 1 plus A, 1 plus B by lambda square, and this is what is normally found for n for all those dispersive glasses that I had shown right in the first slide. And this is called the Cauchy formula. And so A is a coefficient of refraction and B is called the coefficient of dispersion. All right. From a very simple model of spring, mass and spring, I've been able to obtain, which was really obtained by Cauchy simply from experiments. Okay, by fitting the data. Okay, but we can recover this observed behavior from that simple model. So how does a frequency dependent look like? So you can see that this is plotted on a huge log frequency. So in very low frequency, there can be the dipole constant depends on space charge. Then there is dipolar orientation. And then there are ionic. You can see anomalous dispersion around ionic, okay, where ions, let's say NaCl or KCl. And then this is, well, light frequency, 10 to the power 15 frequency light, this electronic polarization. Okay, so for very small frequency, okay, everything contributes. But as I'm going increased frequency, then then they can't respond. So dipoles can't respond to light frequency. So I drop my epsilon r. So ions are very heavy. They cannot respond to almost light frequency. Is only electronic can respond to the light frequency. Okay, I'll have problems in the home assignment trying to decide. And then corresponding to each loss, I have loss, dielectric loss. Okay, each method I have a ionic loss. There is a loss. Okay, so frequency dependence of polarization from almost DC to light frequency for a typical dielectric. Okay, so that is what has given us a complete description of electromagnetic waves with epsilon and sigma. All of them can become complex. Okay, a refractive index itself can become complex because I'm taking into account both propagation and loss. So we have now done everything: electromagnetic waves in vacuum, electromagnetic waves in lossless dielectric, electromagnetic waves in a conductor, which becomes like a dielectric at very high frequency, and in a lossy medium within a dielectric, in which we have been able to use the wave equation and make the convenience of making sigma, epsilon, everything as complex, and hence retain the real terms and the lossy terms together for our analysis. Okay, so with that, I think I've finished all the